This video is a step-by-step solution for the example entitled Evaluating Energy Transfer Rates of a Gearbox at Steady State. In this example, you will learn about performing the energy balance at steady state for a gearbox where the rate of convective heat transfer from the gearbox accounts for the difference between the input and the output power. Let's look at the problem statement. During steady state operation, a gearbox receives 60 kW through the input shaft and delivers power through the output shaft. For the gearbox as a system, the rate of energy transfer by convection is Q dot is equal to HA times TB minus TF, where H equals 0.171 kilowatt per meter square Kelvin is the heat transfer coefficient, A equal 1 square meter is the outer surface area of the gearbox, TB is equal to 300 K or 27 degrees C is the temperature of the outer surface, and TF equal 293 Kelvin or 20 degrees C is the temperature of the surrounding air away from the immediate vicinity of the gearbox. For the gearbox, evaluate the heat transfer rate and the power delivered through the output shaft, each in kilowatt. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. During steady state operation, a gearbox receives 60 kilowatt through the input shaft and delivers power through the output shaft. For the gearbox as a system, the rate of energy transfer by convection is given by Q dot is equal to HA times TB minus TF, where the value of H, 0.171 kilowatt per meter square Kelvin, is the heat transfer coefficient, A equal 1 square meter is the outer surface area of the gearbox, TB is equal to 300 Kelvin is the temperature of the outer surface, and TF equal 293 Kelvin is the temperature of the surrounding air away from the gearbox. For the gearbox, evaluate the heat transfer rate and the power delivered through the output shaft, each in kilowatt. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement, presented here in a bullet list format. A gearbox operates at steady state with a known power input. An expression for the heat transfer rate from the outer surface is also known. The next thing is to summarize what we have to find. This is the same information we highlighted in green in a critical read of the problem statement, presented here again as a bulleted list. Determine the heat transfer rate and the power delivered through the output shaft, each in kilowatt. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few key pieces of information which will help with our solution. The first thing to note is there is no mass entering or leaving the gearbox. This immediately suggests that a closed system approach is the proper one. Having recognized this important fact, let's select a system boundary. Remember that for a closed system does not allow any mass in and out through its boundary, so following a physical boundary makes sense. Here, the system boundary is selected to follow the physical boundary of the gearbox as delineated on the schematic with the red dashed line. It ties in all the information provided to the information requested, namely the input shaft and the power provided, the temperature of the boundary of the system and its area, the temperature of the air surrounding the gearbox and the convective heat transfer coefficient, and finally, the output shaft with its unknown power to be found. The next step is to develop an engineering model. In other words, listing a set of simplifying assumptions which will allow us to perform the analysis of the problem. The gearbox is a closed system at steady state. and for the gearbox, convection is the dominant heat transfer mode. Having completed all the required initial steps for our problem solution, let's develop the analysis. Using the given expression for Q dot, the rate of energy transfer by heat, Q dot is equal to minus HA times TB minus TF. After substituting the known numerical expression for the parameters, we obtain the following, which gives us a value for the heat transfer rate of Q dot is equal to minus 1.2 kilowatt. This is the first answer we were seeking. Note that the minus sign for Q dot signals that the energy is carried out of the gearbox by heat transfer. That is, an energy loss from the gearbox to the environment. Having determined the energy loss by heat transfer, we continue our analysis by applying the energy rate balance for the gearbox as our system. At steady state, this energy rate balance reduces to dE over dt is equal to Q dot minus W dot, where the unsteady term dE over dt is equal to 0. This expression reduces to W dot is equal to Q dot. The symbol W dot represents the net power from the system. The net power is the sum of the input power W1 dot and the output power W2 dot as shown here. With this expression for W dot, the energy rate balance becomes W1 dot plus W2 dot is equal to Q dot. Solving for W2 dot and inserting Q dot is equal to minus 1.2 kilowatt and W1 dot equal minus 60 kilowatt, we obtain W2 dot is equal to Q dot minus W1 dot. In the above expression, note that the minus sign is required because the input shaft brings energy into the system, hence it is negative by sign convention for work or power. Substituting the given value for the input shaft power and the value we calculate for the rate of heat transfer, we obtain W2 dot is equal to minus 1.2 kilowatt minus 60 kilowatt, which gives us a value of W2 dot is equal to minus 58.8 kilowatt for the output shaft power, which is the second answer we were seeking. The positive sign for W2 dot indicates that the energy is transferred from the system through the output shaft as expected. In closing, I would like to make a few comments. In accord with the sign convention for the heat transfer rate in the energy rate balance for a closed system, the empirical expression for the convective heat transfer is written with the minus sign. Q dot is negative since TB is greater than TF. That is, heat is flowing out of the gearbox at TB into the environment at TF from hot to cold. The properties of a system at steady state do not change with time. The energy E is a property, but the heat transfer and the work are not properties. Finally, for the system, the energy transfer by work occurs at two different locations and the signs associated with their values differ, minus at the input and plus at the output. At steady state, the rate of heat transfer from the gearbox accounts for the difference between the input and output power. This can be summarized by the following energy rate balance sheet in terms of magnitude. On the energy input side, we have the mechanical shaft power. On the energy output side, we have the mechanical output shaft power and the heat transfer loss to the environment. Both the input and output columns add up to the same numerical value of 60 kilowatt, which shows that we did not make any mistakes and the total energy in the system is conserved. In summary, in this example, we have learned about evaluating the rate of convective heat transfer from a gearbox given known temperatures, heat transfer coefficient, and surface area, and then applying the energy balance of the gearbox at steady state to determine the output shaft power. This concludes the step-by-step solution of the example entitled evaluating energy transfer rates of a gearbox at steady state.